This chapter is called The Cutaneous Senses, and so we're going to talk mostly about just touch and pain, and I'm going to start by talking about touch. The somatosensory system includes the cutaneous senses that are responsible for our perceptions, that are anything stimulated by the skin. So touch and pain are what we're going to talk about. I'm going to ignore itch, tickle, temperature, those things. The cutaneous senses are involved with the grasping of objects. They protect us against damage, and they also motivate sexual activity. So various places, various authors ask, which sensory system would you be most willing to give up? Which would you'd be least willing to give up if you had to lose a sensory system? And most people think, well, vision and hearing are extremely important, and we tend to take the somatosensory system and the chemical senses as well, the taste and smell. We kind of tend to take those a little bit for granted, but this motivating sexual activity is really important, as is the protection against damage and grasping objects. And so I'm going to talk a little bit about Ian Waterman when we get to talking about this, and I think it becomes clear how integral this is to our lives, that these things that we don't think about. Included in the somatosensory system that I won't talk about very much at all are proprioception, so the position of the body and the limbs. We have these proprioceptors that are telling us about that, and then kinesthesis, the movement of our body and limbs. Those proprioceptors are telling us about movement as well. And in addition, our vestibular system is really influencing both proprioception and kinesthesis, and vice versa. Those systems are influencing our vestibular system, which is that part of the inner ear that kind of tells us where our head is and how we're moving, and so is part of our sense of balance. I have this quote from Edward Pearl: "When you watch a baby touch, you are watching the development of intelligence in his or her cerebral cortex." So very early on, this is how we learn about the world. And babies have particularly sensitive tongues. They like to put things in their mouths because that's how they learn about the world. And we really are watching the development of their intelligence as they are feeling things. A couple more points under the importance of touch here. So one comes from Tiffany Field, looking at the positive effects of touch and massage. Tiffany Field works at the National Touch Institute in Miami, and she is one of the reasons really why we have the kind of prenatal care that we have in these days. So her study was that they randomly assigned premature babies to either kind of standard care, which was being in one of those, basically an incubator where they're kept safe and they're kept warm, but they really don't have anybody touching them, versus the standard care plus, I think it was 3 15-minute massages a day. And those premature babies that got those 3 15-minute massages per day, again, randomly assigned, those babies went home earlier, they gained weight faster, they got out of the hospital faster. And so that became the standard care. And it looks like what's happening when we're massaging those babies is that it's stimulating the vagus nerve, and it's allowing for them to take in the nutrients of their food better, more efficiently. But she's also looked into this question for adults as well. Mary Carlson comes from a different kind of perspective in looking at this question, and she has looked at the negative effects of not being touched. And so instead of having a true experiment, this is one of those what they call natural experiments that was set up kind of in the world, and I'm uncomfortable calling them experiments, as she went and looked at the children who were in these overcrowded orphanages in Romania, where really they were so overcrowded that all the nannies or the workers could do there is they would just prop up the bottle, prop up the bottle, prop up the bottle, go and do their propping up the bottles for the infants. You know, they have infants and children of all ages. Then they come back around and they take down the bottle, So they're not really, it doesn't look like they are really interacting with those children at all. And those babies are not being touched. And those children that are coming from those orphanages were, they have smaller stature altogether, and they have smaller brains, and it influences their cognitive ability, their intelligence, and their social ability as well. Like that has some confounds in it because it is a natural experiment, but it's still really quite telling. So some facts about the skin. It is called The Monumental Facade of the Human Body by Comel back in 1957. It is our heaviest organ, our largest sensory system. It prevents body fluids from escaping from our body. It protects our body from all kinds of things, bacteria, chemical agents, dirt, and so on. And it provides information about various stimuli, and that's actually where we're going to spend our time, is talking about the kind of stimuli that we get information about through our skin. It is made up of the epidermis, that outer layer of skin, those dead skin cells, which I know most of us do this in some science class in middle school, I think, where we take a piece of tape or something and we pull it off our skin and we all go, ooh, yuck, those are dead skin cells stuck to the tape. And beneath that we have the dermis. And then within that dermis, either up high close to the epidermis or down a little bit farther, we have the mechanoreceptors that I'm going to talk about, the receptors that respond to mechanical stimulation like pressure, stretching, and vibration. I'm going to talk about 4 mechanoreceptors, and they each have their own properties that that because of these properties, they tell us about different aspects of our experience. So I'm going to start with the Merkel receptors. They are slowly adapting, which is being shown in that picture where it says fires to continuous pressure. So as long as in that little blue bar is the pressure coming on as we go up there, and then you can see it's firing, and the whole time that the pressure is on, the receptor is going to fire. And of course it does eventually adapt and fatigue like our receptors, like our neurons do, but it's going to be slowly adapting. And so as long as I'm touching the table, or if you want to touch something and just think about, as long as you're touching that, those Merkel receptors that are sensing that touch, that pressure, they are responding. And so they tell us about the fine details about things. And so if I'm touching something smooth, there's just going to be this constant firing between all of them. But if sometimes I get the wire rings on my notebook, and if I'm touching something that has those kind of grooves, then certain Merkel receptors are going to be are going to be firing more strongly, and some might not be touching anything as I'm between those wire rings, and so they're not going to be responding. So that's going to tell us about those fine details. And then I have the Meissner corpuscle on this slide. So these are rapidly adapting. Sometimes you see the RA up there is rapidly adapting, and what that's showing in that picture then is it fires when the pressure comes on and when the pressure comes off. Okay, and so it's really, those are responding to things like hand grip control. And so when we want to grab, if I want to grab something that is kind of heavy and I want to pick it up, I'm going to have a different kind of hand grip control. And these Meissner corpuscles are going to they're going to fire it when I go to pick that up and grip it with my hand, and they're going to stop firing as I'm kind of holding that and doing things with it. But then when I go to put it back down, they're gonna fire again to inform me of that. And so they're very important for things like, am I holding something heavy? Am I holding something like a kitten or a bunny that I have to be careful with? It's a very important part of our perception. Oh, and I left off on that slide the Merkel receptors and the Meissner corpuscles are up just under the epidermis. So they have small receptive fields as they're up very close to the epidermis. Now, with the Ruffini cylinders and the Pacinian corpuscles, we're going to move farther down into the dermis, and so these are going to have larger receptive fields. Okay, and the Ruffini cylinder is again going to respond to continuous pressure. It's slowly adapting. So the entire time that my hand is stretched around whatever I'm gripping, that stretch of my hands, that those Ruffini cylinders are going to continue to fire and tell me that information. The Pacinian corpuscles are another rapidly adapting mechanoreceptor. So you can see they're firing on when it comes on and when it goes off. And really, Pacinian corpuscles respond to faster vibrations than the Meissner corpuscles. The Meissner corpuscles can handle those kind of slow changes, but fast vibrations are going to be stimulating the Pacinian corpuscles. And so you can think of this as when we feel our car or some kind of motor, refrigerator, or something that's vibrating, that's going to be stimulating the Pacinian corpuscles, but they also tell us about the texture of the textures of certain objects. So sometimes they use sand or something in some of these studies. The texture of sand has as you move your hands through it, it's gonna cause a vibration. Okay, and then I often the top of the rings of the ringed notebook, again, if you move your finger back and forth across that vibration information is going to tell you about really about detail and about texture. So I'm going to go walk through one example of how we use all of these mechanoreceptors all of the time, every day. And so I'm going to use my keys here. And I'm holding my car key in my hand. It's one of those big plastic keys. And so it's smooth. And my Merkel receptors are telling me that this is a smooth part of my key. My Meissner corpuscle is telling me about my hand grip control, so I can keep hold of it given the weight that's falling down. I don't know what I was trying to say. Too far in to stop now. My Ruffini cylinders, which are telling me about the particular kind of grip. So how my fingers are stretched around, because if I like to do this, you guys can see me, but it's one of those kind of wide keys, and I'm holding it so that I kind of have this wider grip on it, so the stretching of my skin. And then I'm going to move to my office key. When I'm holding my office key, I'm going to hold it really differently. It's a small key, first of all. There's a ridge in it, so my Merkel receptors can tell me about that ridge. Actually, if I move my thumb across that ridge, the Pacinian corpuscles are telling me about that. But the keys kind of fall differently from there. The weight behind the keys feels different because of the fact that it is a smaller key and I have to grip it differently. And the way my fingers are stretched around the key is also different. So the grip being different is the Meissner corpuscle. The stretching of the skin being different is the Ruffini cylinders telling me that. And now if I go and I take this key and I put it in my office door and it does that, that's going to be the Pacinian corpuscles telling me about that movement and how that feels. Okay, so there's just one example, again, using these all of the time, every day, in so many situations. So our peripheral nerves are the bundles of nerve fibers that are coming from our skin, are entering the spinal cord through the dorsal root. And so far we've talked about dorsal as being up in the brain and ventral being as down in the brain. But when we get to the spinal cord, because we are bipedal animals, and the way this all works is the dorsal is towards our back and the ventral is towards the front. So the dorsal root is where those peripheral nerves travel, or the way their cell bodies are, and they travel past that and get into the spinal cord through that dorsal horn. And you can see in this picture the medial lemniscus that is marked there, that is going up the spinal cord ipsilaterally up along the same side, and it is actually synapsing I'm sorry, it's actually crossing over, going contralaterally at the medulla in the brainstem. So when we get to the thalamus, it's going to be on the, if I'm touching something with my left finger, that's going to be in the right thalamus, going to the right somatosensory cortex. And you can see where he's pointed out the thalamus, a regular thalamic nuclei we need to go through to get to the primary receiving area, which in this case is called the somatosensory cortex. And if I haven't done this already, somatosensory is the sensory, the sensing of the soma of my body. What's also shown in this picture is the spinothalamic pathway, which you can see it crosses over there at that segment of spinal cord where it is entering. And we're going to talk about that. That's the one that is going to bring up information about pain. And we're going to talk about that pathway when we talk about pain. But right now we're talking about the medial lemniscal pathway. So I'm going to talk about the two major pathways of the spinal cord. I like to start that with the picture because the picture is helpful. But the medial lemniscal pathway, these are our large fibers. This pathway is communicating more quickly. It's a faster communication as these are myelinated large fibers. This is how we get our perception of touch, as well as that proprioception to tell us where our limbs are in space. And again, I'm going to talk a little bit more about the medial lemniscal pathway here as we're talking about touch, and then the spinothalamic pathway where temperature, pain, and itch all go up the spinothalamic pathway. That one has smaller fibers. Some of those fibers, especially for the kind of dull pain, a lot of those fibers are moving a lot more slowly because they're unmyelinated. Some of them are moving, they're all moving more slowly than the larger fibers. It's just that's what happens with the size of the axons, but some of these are actually unmyelinated, and so they're moving much more slowly. Okay, and so again, I have temperature and pain as part of the spinothalamic pathway. I'll put itch in there as well. We see a separation of function between these two pathways, and one of the people, so there are many different people who can show us this, but one of them is Ian Waterman, and he's discussed here as he had, let's see if I can remember the story, everything about what I know about Ian Waterman, because I usually get some questions. He was 17 years old, working in a butcher shop, and he had a fever, got sick, and when he started feeling better, what he realized what happened was his autoimmune system started attacking the fibers in this medial lemniscal pathway. So he lost his ability to feel touch and the ability, that sense of proprioception, so the sense of positions of his limbs. What he ended up doing, because he could not really feel any touch or where his limbs were, was to constantly visually check to see where his limbs were so that he could send a motor command to figure out to then move his limb and then watch where it goes. And then so he had to relearn basically movement, and not based on the information that we usually use for making our movements. And when he had no visual information, it just felt like this kind of floating sensation. So there is a description of him lying in bed at night and just feeling kind of like he's floating. There's also the description of him being in an elevator where the elevator breaks and the lights go off, and when the lights come back on, he's just crumpled to the floor because he needs the visual information to know where his body is and to feel how his body is moving. And so it's really, he was really distraught in that situation. Obviously, he didn't work for a butcher anymore, and this changed his life a great deal. However, in many ways, we're going to say he was lucky because he still had the spinothalamic pathway doing its job. So he was still able to sense pain and temperature. People who cannot feel pain, they usually have a much shorter lifespan, as they'll have something like a burst appendix and not feel it, or they can have frostbite and not feel it. And so they can have pain is telling us about damage that's being done and things that we need to avoid. So they have a much more sort of dangerous life than Ian Waterman. So we have these two major pathways up the spinal cord. Information from both pathways is going to cross over to the other side. If you go back to that picture that was here earlier, the spinothalamic pathway, it crosses over contralaterally in the spinal cord at that dermatome, at that place where the nerves come in. So when we get to the thalamus, they're both contralateral. Okay, most fibers synapse in the ventral posterior nucleus of the thalamus. So there's our thalamic nucleus for this sensory system, and some synapse in other thalamic nuclei. The thalamus is going to do its job of summarizing, filtering, organizing information, and sending that on for higher level processing, right? In the cortex. Then that's going to get sent from the thalamus to the somatosensory receiving area. And I know I've alluded or talked about the somatosensory area a couple of times just at the very beginning of class. Again, feeling the body. This is my primary receiving area for touch and pain and itch and tickle and all of that. And it is in the parietal cortex, in the very anterior and the very front part of the parietal cortex is the primary receiving area. We're also getting information to the secondary somatosensory cortex, or S2, from the thalamus. And we're going to see signals from S1 to S2, and then back from S2 to S1, and to some additional somatosensory areas. We're going to look at the body map in the brain, so the mapping or organization of this somatosensory cortex. This was discovered by Wilder Penfield, who was stimulating points on S1, on the somatosensory cortex, and basically mapped out our body, and he found a somatotopic map, basically a body map. Sometimes or often called the homunculus, which is Latin for little man. And you can see there's kind of a little man in our body map there as we are. So if we go as dorsally as we can and medially towards the center of the brain is where I'm feeling. So down there's my genitals and my feet, and then I have some space for my legs and my body. Not a lot of brain space, you'll notice. And then a little bit for my overall head, and then my arm. And I'm going to spend a little time here as we're moving out, kind of laterally, maybe coming ventrally down a little bit for my hand and my face, and especially if you see the lips. And I'm going to even include the tongue in there as being as having a good amount of representation. And I'm going to talk about that as cortical magnification, which should sound familiar. We talked about the cortical magnification of the fovea, that having that more representation in the brain, part of that was the part of what gave us the acuity of the fovea was the one-to-one wiring, but it also, that one-to-one wiring gave us this cortical magnification, that we had more representation, more space of our brain was representing the foveal vision. Well, we see that in touch for our hands, where we want to be able to feel the details of things. We usually use our hands for that. Our lips and our tongue, our mouth are all also very sensitive. When I'm speaking, I am feeling a lot about my articulators, and so we have a lot of representation for those parts of our body as well. When we look at the cortical maps of the body, there is research showing experience-dependent plasticity. This particular study was done by William Jenkins and Michael Merzenich back in 1987. If we look at the monkey's hand there in B, so what they are doing is stimulating that finger and measuring brain activity before and after training. So they're going to train the monkey on a task where they have to use their sense of touch in that finger in order to succeed at the task. Okay, so before training, as they stimulate that tip of the finger, we can see up in A, the activity of the brain is this little area of 2 there, representing that second finger. After training, they go in and stimulate that same little area of the finger, and you can see that there's in the figure C, that there is more of the brain. There's more of the brain that's active in response to stimulating that finger. Okay, so again, experience-dependent plasticity, a change in the brain and its representation of the body based on experience. We have seen this for other senses. We've seen it for vision. We've seen it for hearing.